Okay, what we're looking at here is the electricity and magnetism exam for AP Physics C. This is the 2013 test, question 1, and what we're looking at here is Gauss's law. We're looking at a infinitely long, non-conducting, and then eventually conducting cylinder with some uniform charge density, and we're trying to figure out values of the electric field both inside and outside of this cylinder. So let's take a look at this question and see what we got going on here. We've got a very long, and anytime we see this right here, very long, what they're really talking about is infinite, or nearly infinite. It's non-conducting cylinder, and that's really important because a non-conducting cylinder is allowed to have the charges spread throughout it. We know that for any conductor, most metals, the charges, the excess charges, will be on the outside of it. But this is non-conducting, so the charges can be spread through it. And it has a radius r of a positive charge of a uniform, so it's equal everywhere through it, volume density rho. Section of the cylinder far from its end is shown in the diagram above. So we're very, very far from the ends. The ends are infinite distance away. And let little r here represent the radial distance from the axis of the cylinder. So, either you're inside the cylinder or outside the cylinder distance. And all of our answers need to be expressed in terms of rho, big R, the actual radius of the cylinder, and little r, any fundamental constants we have as appropriate. So, starting off here, using Gauss's law, we're going to just derive an expression for the magnitude of the electric field within the cylinder, so at a radius r of less than the radius of the cylinder itself. And we need to draw an appropriate Gaussian surface on the diagram. Well, there's only a few different Gaussian surfaces we'll be using here. We basically have spheres, cylinders using the soup label, or cylinders using the top or bottom of the cylinder. And for a case of a very long wire, what actually works well to use is the soup label here, or the around part of a cylinder, because we're looking to see the electric field here, which is radiating out of the surface. We're looking to capture it in line or moving normal to the surface of our Gaussian cylinder. And if we draw our Gaussian cylinder here, our Gaussian cylinder is actually just, a cylinder inside of our cylinder. Okay, so this is our Gaussian cylinder here, and maybe we call this length of the cylinder just some length. We'll just call it x. It's some length there. Okay, so that's our Gaussian surface we're using, and if we are trying to set this up for Gauss's law, the way we'll do this is we'll say that the closed path integral, which is really just the surface integral of the region of the cylinder we care about, so that soup label we've got going around the outside, of the electric field dotted with that area of the soup label. And that equals the charge enclosed inside of that Gaussian surface, so inside of our imaginary cylinder we have up here, divided by epsilon naught, the permeability of free space for an electric field. Now, this integral right here, this closed loop integral of this area, that's like a really weird thing to look at, and a lot of people freak out when they see it. But you don't need to freak out looking at that integral. Basically, all this is saying is, what is the surface area of the label going around a soup can? That's all it's saying. What is that area? Well, the area going around a soup can like that is just 2 pi r, because you need to go around a circumference. How wide is your soup can? And then how long is your soup can? So you're going 2 pi r, but then you're bringing it some length. That 2 pi r can be thought of as like the base, and that length can be thought of as a height. When you multiply them together, you get some area. So this is like 2 pi r, and then we called our length here x, so we'll just call it x. And that is what the integral of dA is. So we could write this now simply as the electric field times 2 pi rx equals the charge enclosed over epsilon naught. So I was able to do that calculus there without actually knowing any calculus. I'm just saying what is that area of a specific Gaussian surface. The one we're using here is that kind of label of a soup can. Okay. Now the real issue in this type of problem comes with how much charge are we enclosing within this Gaussian cylinder? What is the charge enclosed there? Well, I know that the charge in general enclosed is equal to the density of the charge in our system. So some charge density, and this is a volume we're talking about here. So, how much charge do we have per unit volume? And then how much volume do we have enclosed within our cylinder? So we've got some imaginary Gaussian cylinder at some radius r. How much charge have you put into that? Well, it's just the density times the volume. This is really similar to the idea of mass. If I had a cylinder filled with dirt and I said how much mass is in that cylinder, well, you could take the density of the dirt times the volume. We're just doing that idea but with charge here. Okay, so this pretty much gets us rho, and then what's the volume of this cylinder? Well, it's pi r squared for an area and then multiplied by a length. So that volume is pi r squared. That gives us an area of a circle, and then we extend that circle for some length. If you're familiar with anything like a CAD system, that'd be like extruding the cylinder. So that's how much charge we have enclosed here. And for this length, we've actually already given the length a different letter. We've called the length here x. So let's just call the length here x. Okay? And we can take this value and stuff it in for charge enclosed. So now what we have is we can say that the electric field here times 2 pi r x equals rho pi r squared x over epsilon naught. And this is awesome. We get a lot of stuff to divide out here. These x's go away. One of the r's go away. The pi's go away. And we find now that the electric field inside the cylinder, so at a radius less than the radius of the actual cylinder itself, well, that's just going to be equal to rho r over 2 epsilon naught. So we can quickly arrive at that solution right there using Gauss's law and setting that up. Okay? So that's how we can do part A here. It's just Gauss's law. It's just a little bit of understanding what area you're trying to use there for that soup label, and then finding the charge enclosed. That's the other big move there. Okay? Now part B of this problem is asking something very similar here, but it's asking us to find what the electric field would be at a radius outside of the cylinder. So at a radius little r greater than that of the radius of the wire itself. And we're going to use the exact same expression as we did before. We're going to say that the closed integral of the electric field through some area is equal to the charge enclosed divided by epsilon naught. And we are using the exact same Gaussian surface here. We're still using that soup label. So this integral is still going to just be that the electric field times 2 pi r x equals some charge enclosed over epsilon naught. Now just like before, we have to ask ourselves, what is our charge enclosed here? Well, our charge enclosed this time is the charge density times the volume of the cylinder itself. So we're drawing now, our Gaussian surface is all the way out here. We're on the outside of our system. So the charge enclosed is just what is the volume of this cylinder right here. That's the volume we care about. So we can just say that the charge enclosed is equal to rho times pi, and the radius we care about that has all that charge in it is just big R, the actual radius of the cylinder, squared, times some length, which we've just called that x. So we take this, we plug it back in for the charge enclosed, we get that the electric field times 2 pi rx equals rho pi big R squared x over epsilon naught. And it's important for us to recognize that the lowercase r and the capital R, they're different R values. The lowercase r is, you're moving that electric field farther and farther away, that point you care about, farther away from the axis. But that big R value, it's just the radius of the wire. So it's some constant value there. So when we go and we try to cross some stuff out here, the x's still go away, the pi's go away, but the r's do not. The r's stay there. They're different values of r. And what we see is we see that the electric field outside of the wire, or at some distance r greater than r, is equal to rho big R squared over 2 epsilon naught little r. Okay, so a similar solution, but slightly different there. And it's because those r values, big R and little r, are different quantities. We need to be careful about that. Part C, it's asking us on this little graph here to sketch the graph of the electric field as a function of the radial distance, little r, from r equals 0, the center of the cylinder, all the way out to twice the radius of the actual wire. And we need to explicitly label any intercepts, asymptotes, maximum, minimum, numerical values, or algebraic expressions, which really, we're just going to have algebraic expressions here because we don't have any numbers yet, as appropriate. So what we need to do is, first off, whatever you get for your solution, if you got what we got, congratulations. If you got something different, follow whatever it is that you found. Okay, whatever weird thing that you came up with because you might have messed up some math or you forgot what you're doing or you just took a guess, graph what that is because you're being consistent to what you found there. For what we found for our answers, we see that this value here inside the electric field, when r is less than the radius, it increases with r to the first. So it increases linearly. So we're going to have a linear line here, and it's going to increase like that all the way out to this point where we have capital R, because that is to the edge of the cylinder itself. Now, the point it's going to reach here is as follows. If we take this value of big R and we put it in for little r here, we're going to get a value there, that top peak of rho r over 2 epsilon naught. That is the peak value this can obtain. So we're just going to label it on that graph as this is rho r over 2 epsilon naught. Okay? And that corresponds to that peak there at that point r. Now afterwards, how does this change? Well, once we get outside, what happens is rho is still a constant, this big R squared is a constant, and 2 epsilon are constants. So what's really happening here is we are decaying, or this electric field is proportional to some value 1 over r. So we're actually going to lose electric field here as a function of 1 over r. So this is going to just decay down something like that, okay? So it's going to decay as 1 over r. So I just kind of drew a curve down like that, opening up, okay? So that's how we can figure out part C. Now, for part D, we're asked to find a potential difference. And a potential, remember, is a voltage. So we want a voltage here. So how can we do that? Well, anytime we have electric field information and we're asked to go to a voltage, or we have voltage and we're asked to go to electric fields, we should be thinking about the equation that the electric field is equal to the opposite of the derivative of the voltage as a function of distance. And in our case, our distance is radial, it's dr. Now, this is the differential form of writing this equation. What we can actually do to make it a little bit more straightforward is if we bring the negative in the dr term to the other side, we can then integrate both sides of this. And what we see is that the integral of dv just gives us v, and that has to be equal to the negative integral of the electric field moving with radial position. So if we're just going from r equals 0 to r equals r, then what they've provided us is they've provided us with boundaries here from 0 to r for this function. And that means we're inside the cylinder. So this electric field is the electric field inside the cylinder, which allows us to rewrite this as the negative integral from 0 to r of rho r over 2 epsilon naught dr. And this is actually an integral that hopefully you feel very comfortable with. The rho, the 2, and the epsilon naught are all constants. You can pull them outside. And what we're really just looking at here is what is the integral of r dr. Well, if we run this integral, I'll pull the rho over 2 epsilon naught outside. And when I do that and I run the integral, we're going to get r squared, so we've added 1 to the exponent, and then we divide that exponent, so divided by 2. And then I need to bound that from big R to 0. When I bound this, I do upper minus lower, or top minus bottom, however you like to think about that. And we're plugging in these values of r and 0 in for our lowercase r, because that was the quantity we're changing. So when we write this out, we can write it as rho over 2 epsilon naught times the quantity big R squared over 2 minus 0. And you know what I dropped on accident? I dropped that negative on accident. So I need to make sure I bring that negative through there. Make sure you're not dropping your negatives anywhere. That's a boo-boo. And what we see is that the difference in the potential from one spot to the next is simply a value of, negative rho r squared over 4 epsilon naught. The 2 and 2 make 4. Now they're asking for a magnitude, so if you did erase that, you're right. You're just looking for a magnitude, but if you have it as the negative, you should be fine there. Now the next part of this question is asking us, is the potential higher at r equals 0 or r equals r? That's a weird thing to think about there. But we actually have it pretty straightforward to answer this. Well, if you don't know, it's a 50-50 shot, so pick one. If you leave it blank, you're doing yourself an injustice. But we actually have a good idea for this. If we go back to our derivation or our integral here, and we look at it right here, well, what we're looking at is if we carry this negative throughout this, so I'll place my negative and I'll apply it to both of them. So that's a negative, and then the negative of a negative is a positive. When I look at this, this right here, this is the potential at r. It's some negative amount. If I go at the center, r equals 0, my potential is 0. So what is a larger number? 0 or a negative? What's a higher potential? 0 or a negative? Well, 0 is actually your larger amount there, because negative you're taking away. So we actually have a higher potential at r equals 0 there. So that's kind of a neat thing, just by looking at what we've done previously in that integral. And that wasn't a bad integral to do. This is probably one of the more straightforward integrals that you can see on a test like this. So that's nice. The very last part of this, we've taken the non-conducting cylinder, and that was important before because the non-conducting cylinder could have the charges spread throughout it, and we've replaced it with a conducting cylinder. And as I stated before, a conducting cylinder, or any property of a conductor, is that the excess charges lie on the outside of that conductor. And it's the same shape, it has the same linear charge density, which that should be a telltale right there, because now there's not charge throughout the center of the cylinder, there's only charge on the edge. Okay, so this is a linear charge density, and that's a little tell right there. And what we're asked to do is on the axis below, sketch the electric field E as a function of r for r equals 0 to r equals 2 over r. And we're labeling any intercepts, asymptote, maxima, or minima with those numerical values. Okay? Well, the first thing we should immediately know, and this is just fact, is if you are inside of a conductor, something like a metal, there is no electric field inside the conductor. And that's simply because the excess charges are on the surface of the conductor. That means that no matter what you draw for your Gaussian surface on the inside, you can't enclose any charge. And if you can't enclose a charge, your E field is going to be 0. So all on the inside of this, so from 0 to r, you have no E field. As soon as you hit the edge of the conductor and go outside of it, you immediately gain an E field, and we know how that E field is going to decrease on the outside of the conductor. It's going to decrease just as we found before as this 1 over r value here. Okay? Now, what is this point right there? Well, if it has the same linear charge, then that means it has the same charge per unit length as it did before, which means that this value here is just whatever value we found for our previous graph right here, okay? Because the only thing that's changed is this beginning segment. The rest of it is the exact same. So we can just say that this beginning segment here, or this point that we get to, this is just rho r over 2 epsilon naught. And that's it. And that's a really big idea there. If you're in a conductor, there's no electric field. There's no charges that you're containing on the inside, so you can't use Gauss's law in there. It just gives you a flat 0. Okay? So that's a big takeaway there. That's what they're looking at for that type of problem. Okay? So with that, that's a quick Gauss's law, and that's a really great problem. It's a cylinder with charges throughout it. We're just using Gauss's law. Remember, whenever you're doing that, it's not a tough integral. You're just saying what is the area in which this electric field, this electric flux is moving through. And with that idea, you can quickly get some really easy answers here. Okay? So that was, once again, the AP Physics C E&M exam question from 2013, question 1. I hope you like that solution there on what we did. But with that, this problem is finished.